All right, today we're diving deep into the secrets of milling. We're going from a raw, solid block of metal all the way to a complex, finished part with just unbelievable accuracy.
You know, it really does seem like magic, doesn't it? How do you take a simple chunk of stuff and sculpt it into something so incredibly precise? Well, the answer? It's part art, part science, and really, it's all about control. So let's pull back that curtain and see exactly how it's done.
And this right here, this is our main tool, the vertical milling machine. I mean, this thing is just a beast, an absolute powerhouse of versatility. The whole idea is to remove metal by spinning a cutter with multiple teeth into what we call the workpiece. That's just the fancy name for the raw material we're shaping. This is where all that transformation really kicks off.
Okay, so you'd probably think the real action starts the second the cutter touches metal, right? But here's the thing. The most critical work, the stuff that really counts, happens way before the machine even makes a sound. It all boils down to an incredibly meticulous setup, where literally every single detail matters.
So let's take a look at the machine's anatomy. Up top, you've got the spindle. That's what holds and spins the cutting tool at some serious speeds. Then there's the quill handle, which lets you move that whole spindle assembly up and down, kind of like for drilling. And then these handles here, they control your X, Y, and Z axes, so you can move the table left and right, front to back, and up and down. It's like a three-dimensional dance, all about precision.
But look, none of that fancy movement means a thing if the machine isn't perfectly, and I mean perfectly, aligned. The head, that's the part holding the spinning tool, it has to be completely perpendicular, or what we call square, to the table holding the part. And this isn't just a good idea, you know. It's the absolute, non-negotiable foundation of any precision work.
And yeah, there's a name for that process. It's called tramming. It can be a real pain for sure, but it's an absolutely critical step. You're basically just adjusting the head until it's perfectly square to the table in both directions, the X and the Y. The best way to think about it is like tuning a guitar before a big show. If you skip it, nothing you play is going to sound right. Same idea here.
And here's a great look at exactly what happens when you don't tram properly. That perfect circle you were trying to cut, it ends up looking like a C. Those nice flat surfaces, now they've got these little uneven slopes. And imagine this is a part for, say, a jet engine. A tiny error from a machine that wasn't trammed could lead to a total disaster. The machine is essentially lying to you, and your expensive part, it's headed for the scrap bin.
All right, so the machine is trued up and ready to go. Now we gotta hold our material, and hold it tight. And for that, we bring in the king of work holding, the vise. But don't be fooled, this is way more than just a simple clamp. This thing has some serious superpowers.
So, superpower number one, the fixed jaw. It's this perfectly flat, precision-ground surface that acts as a totally solid reference point. That way, all of our measurements have a reliable place to start from. Superpower number two, it gives you total access to the whole top surface of your part. See, it holds the piece securely from the sides, leaving you free to machine whatever you need on top with nothing blocking your way.
Okay, so the physical setup is done. The machine is perfectly square, the part is locked in tight. But even the best setup in the world is totally useless if the machine has no idea where to cut. We've got to give it a map. We have to speak its language.
And that leads us to the next big question, right? In this whole world of automated machining, how do we get our ideas, our human intent, translated into a set of precise, repeatable actions for the machine? How do we actually tell it what to do?
Well, the answer is something called G-code. Think of it as the native language of CNC machines. A single, simple line of G-code, something like G01, X10, Y20, F100, that's just telling the machine to move in a straight line to a specific spot, X10, Y20, at a certain speed. And believe it or not, every complex curve, every perfect hole in a finished part is built from a long sequence of these seemingly simple instructions, all executed with just flawless precision.
So we've got our instructions loaded in. It is finally time. This is the moment of truth, you know, where all that careful prep work is about to pay off. It's time to make the chips fly and actually start carving up our material.
And when it comes to the science of the cut, it really all boils down to two key things: speeds and feeds. Speed is just how fast the tool is spinning, the RPM. And feed is how fast you're moving the material into that spinning cutter. Getting that balance just right is absolutely crucial. It's what gives you a clean cut, a beautiful surface finish, and it makes your tools last a whole lot longer. And wow, this table really shows you just how dramatically that balance has to change depending on what you're cutting. Just look at the difference. The recommended cutting speed for aluminum is almost 7 times faster than for steel. It's like every material has its own unique personality, and you have to learn how to work with it, adjusting your approach every time.
And you know, this isn't guesswork at all. It's pure math. Machinists use formulas exactly like this one to figure out the perfect spindle speed and RPM. They take the recommended cutting speed for a material, that's VC, and they factor in the diameter of the cutting tool, which is D. It's actually a pretty beautiful thing, turning these scientific principles into precise, real-world action on the machine.
But it's not just about how fast you're going. It's also about which way you're going. See, there are 2 basic strategies for how the cutter meets the material. You've got conventional milling, where the tool spins against the direction you're feeding. And then there's climb milling, where it spins with the feed. And trust me, the choice you make here has a huge, huge impact on the final part. So with conventional milling, the tool is spinning against the feed, kind of scooping up the material as it goes. But in climb milling, the tool spins with the feed, almost pulling itself into the cut. Now, climb milling usually gives you a way better surface finish, and that's because the chips get thrown out behind the cut instead of getting crammed into the nice new surface you're making. But there's always a but, right? Conventional milling is often your best bet for really rough materials, like cast iron, because it engages that tough outer skin a bit more gently.
Okay, the chips have flown, our block of metal is now apart. But we are not done yet, not by a long shot. In fact, one of the most scientific parts of this whole process is just started. We now have to verify that the thing we made is actually the thing we intended to make.
At this point, we're working on a scale that's almost impossible to imagine. We're talking about microns. A single micron is 1,000th of a millimeter. And in high-stakes fields like aerospace or medical device manufacturing, these tiny, tiny measurements, they're literally everything. And that brings us to the idea of tolerance. A typical part might need to be accurate to within plus or minus 5,000ths of a millimeter. I mean, that is an insanely small margin for error. To put it in perspective, we are talking about dimensions that are many, many times smaller than the width of a single human hair.
So how in the world do you even measure something that small? You obviously can't just grab a ruler. No, you need a whole arsenal of super specialized, incredibly accurate inspection tools.
And this is really just a peek into that arsenal. You've got your traditional but still super precise tools like micrometers, but then you get into the really high-tech stuff like coordinate measuring machines, or CMMs for short. What a CMM does is it uses this ultra-sensitive probe to touch the part at hundreds, sometimes thousands of points. It builds this perfect 3D digital model of the part, which you can then compare to the original design, with an accuracy down to a single micron. It's just mind-blowing.
So there you have it. We've gone from a simple, solid block to a fully verified, high-precision part. We've walked through the meticulous setup, the digital language that tells the machine what to do, the science behind the cut itself, and finally, that microscopic verification process. And it all leads to one last really fascinating question to think about. As these machines get smarter and more automated, what's the future role for human craftsmanship in this incredibly intricate dance of precision?